As of now, we have already discussed about logistic regression, and now we are going to discuss about neural network. This network is similar to the brain model. That's why we are calling this as a neural network. Already we have extensively discussed about neural network in the machine learning. Now we are going through the basics to implement it in the deep learning. Assume that I am taking a training sample, one training sample. In that training sample, we are having three features. By using these three features, we are calculating the Z, and by using that Z, we are calculating the A, or predicted output. This is what we have done in the logistic regression. We will implement that here. So initially, we have taken a X. In this X, there are three features are there, X1 and X2, X3. And W, in this W, there are three parameters. Because we have taken three features, the parameters will be also three only. Now this is B. So Z is equal to W transpose X plus B. From this Z, we are calculating the A. By using this A, we are calculating the loss function. So whenever we want to know what is the rate of change of W and B with respect to loss function, then by using the back propagation, we are calculating that. So to predict the output, we are using the forward propagation. To calculate the differentiation of the loss function with respect to the parameters, we are using the back propagation. This is a neural network. In this neural network, you observe there are two layers. This is layer 1, this is layer 2. This is also input layer, but generally when we talk about how many layers are there in this neural network, we will say there are two layers. So in this neural network, this is called as input layer, and this is called as hidden layer, and this is called as output layer. Why it is called as input layer? Because in this layer, the three features are the input features. We are already giving them to the neural network. Why this is called as a hidden layer? Because we don't know what is happening here. We can only see the output finally. So that's why we are calling this as a hidden layer. It is like simply you take a calculator and perform some addition or subtraction or multiplication, but you don't know what is the program that is written in the calculator. But you can simply see the output. You wonder how the calculator is calculating it, because behind there is a program. That is the hidden program. Similarly, we don't know what action is taking place in this layer, but still we are getting some output. That's why this middle layer is called as hidden layer, and the output we are seeing, that's why we are calling this as a output layer. This output is a predicted output. Now I am representing x1 and x2, x3 with a single x. This x is a matrix consisting of three elements. Because in this matrix three features are there, now I am taking W as a matrix with three features and B. Why I am using the superscript 1? Until now in the logistic regression we have not used any superscript concept, but why I am representing W superscript 1? Because this time many parameters are coming. The parameters that are representing in between the input layer and the first layer, the parameters that are representing first layer and the second layer. What are these parameters really? These parameters are deciding, in generally in the neural networks we can also call them as weights. These weights are actually deciding what is the activation unit's output. So these weights are useful to calculate the activation units. These parameters are very useful. So you observe here, from the each x1 and x2, x3, from each feature there are three wires are going for each and every activation unit. So each and every feature is an input for each and every block in the first activation layer. On each arrow there is a weight or there is a parameter. This is what we are calling as a parameter. We want to represent all these parameters in a single matrix. So from x1, how many wires are going? There are 4 wires. From x2, how many wires? There are 4 wires. From x3, how many wires are going? 4 wires. Totally 12 wires are going. We want to represent all these 12 wires. On every wire, there is a weight W. So we want to represent these 12 weights in a single matrix. That is the W superscript 1. How we will represent? We will represent by using a 4 by 3 matrix. This 4, here it is a 3 by 3 matrix. Sorry, we have not taken only, not 4 activation units. We have only taken 3 activation units. So here 9 wires. Because from x1 3 wires, x2 3 wires, x3 3 wires, so 9 wires. The weight, the parameter matrix is represented by W 3 by 3. We are using the superscript 1 to denote that it is the parameter matrix. It is the weighted matrix which is controlling the activation units of the first layer by using the input features. So similarly, this B1 is similar to the concept of X0 that already we discussed in the machine learning. Okay, by using this B and by using this X1 and X2, X3, and we have W superscript 1. Now we can calculate the activation units. That's what we are doing here. Now we have calculated the activation units of the first layer. After calculating the activation units of the first layer, because it is a logistic function, the outputs of the first layer must be, every black output must be in between 0 and 1 only. Again, these outputs are given as inputs for the second layer. So these outputs are given as inputs for the second layer. So now you observe, it is a W superscript 2. Now the parameters of the second layer. Now W superscript 2 into A superscript 1, because we are multiplying with the previous layer activation units, plus B2. From this Z2, we are calculating the predicted output A2. To calculate the predicted output, we are using the same forward propagation. Even though we have hundreds of the layers in the neural network, we will go with the same procedure. First, we will calculate the Z1, from that Z1, A1. And again from that A1, Z2. And from that Z2, A2. From that A2, again Z3. And from that Z3, A3 again, so on and so on, Z99. From that Z99, A99. From that A99, Z100. From that Z100, A100. This is the forward propagation we already discussed. So from the final layer, we are getting the expected output. Now we are checking whether this expected output is similar to the predicted our original output or not. So this predicted output, if it is whether it is near to our original output or not. For that, we are using loss function. Because we are using only one training sample, I am not calling it as a cost function. Cost function when we deal with the M training samples. At present, I am only dealing with single training sample. That's why I'm calling it as a loss function. Now I want to know how these parameters are affecting the loss function. It is useful for me to calculate the differentiation when I use the gradient descent. So again, I am going the back propagation. So first I am differentiating dou L with respect to A, and A with respect to Z, and Z with respect to A1, and again A1 with respect to Z1. This is called the back propagation. So by using the back propagation, we are calculating the differentiations. By using the forward propagation, we are calculating the predicted output. So whenever you want to know how the parameters are affecting the loss function, why we are not calculating how the input features are affecting the loss function? Because we do not have the capability to change the input features. So we are not at all concentrating to change the input features. But in our hands, there is a chance to change the parameters. That's why we are checking. By considering which parameters the loss function becomes minimum. That's why we are checking how is the effect of these parameters on the loss function. So we are checking to check there is we cannot check directly. We cannot take dou L by dou W1, we cannot take directly. That's why we are taking in single steps. First we are calculating dou L by dou A, dou A2, from that dou A2 by dou Z2, from that dou Z2 by dou A1, from that dou A1 by dou Z1, from that dou Z1 by dou W1. This is how we are going. That's why it is, we are calling this as a back propagation. Now again we have taken two-layer neural network. This time in the second layer we have taken 4 activation units. Sorry, in the first layer, whenever I am using the terminology in the neural network, this is the first layer and this is the second layer, I can call this as a 0th layer. Okay, in the first layer we have 4 activation units. In the second layer we have only 1 activation unit. So as we discussed, this is called as input layer, and this is called, because here in the input layer all input features are there. This is called hidden layer, because we do not know what is happening really in this layer. And final one is output layer. We are getting the predicted output. Remember, this is not the original output. Now we are representing this as a superscript 1 activation units I am using. That's why a superscript 1. In this a superscript 1, again there are 4 values are there. So we discussed this as a 2-layer network. From these 4 activation units, we are getting the predicted output. Now we already discussed, by taking the simple input features, we cannot calculate the activation unit functions. We require the parameters W. So here I am taking this as X naught in the machine learning, or I can call it as a B. Okay. Now from this X naught also, 1 wire is going for every activation unit. Okay. So remember, in this W, we have from X1 we have 4 wires, from X2 we have 4 wires, and X3 4 wires are going to the activation units. So totally 12 wires. And on each wire there is a parameter that we are representing by using the W. So on the 12 wires there are 12 parameters. We are representing that as a W4 by 3, 4 rows and 3 columns. The rows are the rows of the parameter matrix are decided by the present layer, and columns are decided by the previous layer. Or we can tell the rows are represented by next layer, the columns are represented by the previous layer. According to our convention we can take, there is no problem. Similarly, now if I take the parameters here, parameter matrix here, now it is 1 by 4. The rows are represented with this layer, and columns are represented with the previous layer, we can tell. This is how we represent a neural network by using the parameter matrix W. And here we have separated the B. Remember, that is the only difference. That's we discussed in the machine learning. And here, there we have considered X naught as an inclusion, but here we separated B intentionally. We separated B in the neural network representation, but output will not differ. Output will not differ. Only conventionally they may look differently, but the process is the same.